Guys, let's finish talking about extrema. So what I want to do today, we've talked about the extrema and how to figure out like what they are, if they're maxes or mins or relative or absolute. But today I want to show you how to find the actual value on your calculator. So this should be easy. It seems like we've done it. I'm not sure if we have. Have we done left bound, right bound on your calculator? Yeah. Okay. So I'm going to just show you quickly. Let's say I have, oh gosh, I don't know. Let's do y equals, we'll just do a parabola. X squared plus 3x plus 2. And I'm doing an analysis on this, okay? And you'll want to follow along on your calculator to make sure that you can actually find this, all right? Whenever I type it in, x squared plus 3x. I know we found the zeros, but I don't think we found the max and mins, but it's the same concept. All right, so what I want to do, if I want, it is toasty in here.
Yeah. The air just turned it off.
Here's what I want to do. If you go second trace, the same way we went in to find the zeros, okay? Does this graph, did it have a max or a min?
No.
A min, right? So I'm going to choose minimum. Okay. Now it says left bound, so you're going to do the same thing. Put your spider pretty close to where you think the minimum is happening, and then click left 3 times. You can go more if you want to. Hit enter. Go back to that minimum or close to where you think it is and hit right 3 or 4 times and hit enter. So you're just giving it an area. You're saying find the lowest point anywhere between those 2 arrows I just put on there. And then you hit enter one more time and it will calculate it for you. Okay. Now here's the thing. Oh no, never mind. So the minimum of this one is negative 1.5. Whoa. Negative 0.25. Is that an absolute minimum or a relative minimum? Absolute minimum. Because it is absolutely the lowest point on the graph. Not mim, but minimum. Does that make sense to everybody how we use the calculator to find it? Left, right, enter. Okay. So left of the minimum or the maximum, enter, then go to the right. I just feel like we've done this. We did it very closely to that whenever you got ice too? Jada, you asked for the directions on that last paper I gave you. It was the directions for finding the zero. It's the same steps for finding the minimum. You just choose minimum, you go to the left of it and then to the right of it. And you do the same thing, okay? We'll keep practicing with it because everything we do, we'll be finding maxes and mins for that. While we're looking at this, is the function continuous? Yes, it is continuous. Is it bounded?
Yes.
Yes, it's bounded. It's bounded below. Good job. What's the domain?
The domain is
negative infinity to infinity. Look at the equation. Does it have any fractions or square roots?
No.
So it's negative infinity to infinity. Look at the graph again. What's the range?
range is negative infinity.
Look at the range, bottoms up. It's always bounded by absolute maxes or mins, which also impacts your range. So if it's bounded, it's got a restricted range. So y'all are absolutely right. The range here is negative 0.25 to infinity. How about, is the function ever increasing? Yeah, where is it increasing? What's the interval on which it's increasing?
From that point right there.
From that point to infinity. So we're going to describe it with the x's.
And do the same thing.
So it's increasing from negative 1.5 to infinity. How about decreasing? Is it ever decreasing? Negative infinity to negative 1.5. Y'all got this increasing, decreasing stuff.
Is this stuff like not?
Oh, let's see, decreasing. We'll do a full analysis here in just a minute, and you'll see where we. All right. When we talk about maxes and mins, if this is the min, the way we say this is we say, if this is f of x, we say f of x has a minimum of negative 0.25 at x equals negative 1.5. If we have to put it in words for whatever reason, okay? If you see that wording, understand what that means. That means the point that the minimum is occurring is negative 1.5, negative 0.25. Yes, sir.
Why is this stuff called like extreme?
Because it's extreme points. It's on the extreme end of the graph. Just, I don't know. It just is. All right, y'all ready for symmetry? Let me pause this so you can get your... We're going to do symmetry two ways. We're going to do it graphically, and we're going to confirm it algebraically. Okay? Kind of like with range, we did it one, or domain, we did it one way, but then we confirmed it graphically. All right, symmetry. I have three scenarios for symmetry. I can be even, odd, or neither. So I'm going to run through all three scenarios, then I'm going to show you how to do it algebraically. So the first type of symmetry we can have is even. And you are probably most familiar with this, and you're not familiar to this terminology, but to make it where you can understand it is this means that it is symmetric. Now, what does symmetric mean?
Same on both sides.
Same on both sides. Is symmetric about the y-axis. What does that mean? Same on both sides what? On both sides of the right of the y, right, the y-axis is what divides the graph perfectly. So if I think about something like a parabola this way. Terrible drawing, but you see the y-axis straight down the middle is what divides it, right? It's the same on both sides. If it shifted some, it wouldn't be symmetric about y-axis and it's no longer even. Does that make sense? Maybe? Yes? No? Okay. I'll go ahead and put this algebraically so that we can then look at it also. Algebraically. So that's graphically symmetric about the y-axis. Algebraically, if you have f of x, if you make all the x's negative in f of x, and it still equals what you started with, then it's even. Okay? Okay, let me show you what I mean by that. The equation of this graph that I have here would be f of x equals x squared. Do you agree with that? Okay? That's just the parent function. That's just a quadratic. To verify that it has, now I can look at it and see that it's an even function, right? It's symmetric about y-axis. But to verify algebraically, I would need to come over here and say, well, what happens if I make x negative? Well, if f of x is x squared, then that means I would have changed the x to negative and square it. Well, what happens when you square a negative number? It becomes what? Positive, right? When you square a negative. So look what happens. It gives you back the same thing. If you come back to the same thing, then that tells you hey, it's an even function.
So that's what we check about making it negative?
You check it by changing the x's to negatives, and if you come back to the same thing you started with, it's an even function.
If we did, we mess up.
No, if you didn't, it's not even.
Okay.
Okay? Let me show you one more that comes out even as an example algebraically. Example. Let's say f of x equals negative 2x squared plus 7x to the fourth. Okay? And I was asked, is it even, odd, or neither? Okay? But I was asked to do it algebraically and not graphically. So to do it algebraically, I'm going to take f of x and I'm going to make it negative. Okay? So it becomes negative 2, negative x squared. You got to really watch order of operations here. Okay? Don't multiply negative 2 and 1 and say, oh, that makes it positive. Because what happens here, exponent, this is really like negative 1 in front, right? This exponent's coming around. So I get negative 2. Well, what is negative 1 squared? 1. So this becomes negative 2x squared plus the 7 still here. What's negative 1 to the fourth power? Negative 1 times negative 1 is positive 1. Times negative 1 is negative 1. And times negative 1 again is a positive. Anytime you raise a negative number to an even exponent, it's going to be positive. So I've got plus 7 x to the fourth. Is that the same thing that I started with? Yes. That tells me yes, so this function is even. Does that make sense? So listen, if f of negative x equals f of x, then it's even. Okay, that's how you tell. And that's very important because odd's going to do something completely different. All right, so graphically, what does it do?
It goes down.
Graphically, what does an even function look like? Symmetrical where? The y-axis. The y-axis cuts it in half. Good job. Okay. Algebraically, to prove or to justify or to verify or to show Jerome, put that up, is if I do f of negative x and I get what I started with, then that tells me it's an even function. Okay? Got it?
Yeah.
All right, let's do odd. So I told you there was 3 scenarios for symmetry: even, odd, and neither. Odd. Do y'all remember learning about rotational symmetry? Okay. Odd, the easiest way that I know to tell you with this is if you rotate it 180 degrees, what does that mean? Halfway. Not 360 would be all the way around, but if you rotate it around, twist it around upside down, right? Rotate 180 degrees, it looks the same. The rotation, though, has to be, I should have put this with that, around the origin. What's the origin? 0, 0, right? Right in the middle of the graph. So if you take this, and remember this is graphically, if you take this graph and you twist it around upside down, it still looks exactly the same. It maps back onto itself, okay? Let me show you what that looks like in the form of a graph. If I were able to pick this up and just turn it upside down, it would look exactly the same. It's an odd function. Does that make sense?
Yep.
No?
It would look exactly the same. So you're trying to say
It would look exactly the same. If you did flip it upside down, it would look exactly the same. Think about this thing, taking it and just doing this. if there was a pin in the middle that you could just spin this around, this piece would spin around right down here and look exactly the same.
Okay.
You see what I'm saying? You don't see it? Look at this one.
You know, but so tough if you can just do it, like, if you can
It's-
spin it off the, that would be cool.
It would be cool. Actually, I can show you.
So you trying to feel like, wait.
Let me.
Hear me?
What?
I said you couldn't do this one day because it's not an origin.
Right.
I was just looking at that.
All right. Look at this one. Look at what's going on here. You see this graph? All right. Do you think that's even or odd? Why? Even. You're right. It's even. Why? It's symmetrical. Both sides on the y-axis are the same. Do you see that?
I see that.
Now watch this one. 180 degrees, it maps back onto itself. You see it? That's what you said, didn't you, Silas? You wish you could see it actually move?
Is that all?
So that's an odd function because if you rotate it around, but yes, that's what it means to be even or odd. So we got odd and we got even. Okay? It's got to be the y-axis and the origin. Does that make sense?
So all of them will always have something to do with
Yeah, it's all, yes, it'll always have to be rotated about the origin.
Even y-axis splits it in the middle,
Yep.
and then the odd, the x-axis.
The origin rotates and it looks the same. Okay? All right. So that is graphically, look at the other one I drew here. Even, odd, or no? Odd. If you rotated that one around the origin, I still see your phone behind that cookie box. Well, tell your mother you're doing math right now. Okay. Rotate it around the origin, right? 180 degrees odd. Let me show you what that looks like algebraically. And I know this is a lot, that's why I keep going back and trying to pick up all the other pieces, because when we get done, an analysis is going to take us a full page of everything we're doing, because we got domain, range, boundedness, continuity, symmetry. We got all this different stuff we have to do with these functions, okay?
It's all still the same thing. This is
All right, so algebraically, to show that a function is odd, we're going to do the same thing. If we plug negative x in, this time it's not going to give us the same. This time it's going to change everything. It's going to make the whole function negative. Okay, so everything has to be opposite. Every sign in the equation has to change if it's odd. Okay, let me show you what I mean. If I started out with f of x equals negative 2x to the third plus 7x to the seventh, and I want to know is it even or odd algebraically. So what I need to do is I need to plug a negative in. Negative 2. Now I've got negative x to the third plus 7 negative x to the seventh. So what happens when you raise a negative number to an odd power? It's still negative, right? So this becomes negative 2, negative 1, which would be positive 2x to the third, right? Because a negative times a negative is a positive. Minus, because this is going to make this negative, 7x to the seventh. Now compare the two equations. Look at what you started with and look at what you got. I started here, negative 2 and positive 7. I ended with positive negative. Because everything's opposite, it tells me yes, that's an odd function.
So you can basically see these all in
Kind of, yes, yes, if they're all odd or all even.
I have a question. Okay, so like is it just -1? You just multiply by -1?
Because if the exponent's negative, if the exponent's odd, it's going to keep it negative. So yeah.
So each one you just multiply and then trying to find it. It's even positive.
Mhm. So let me show you one that I want you to do algebraically, okay?
So you have to try out both.
Well, you plug negative x in, and then you look at what you get to see. If you get the exact same thing you started with, it's even. If you get the exact opposite, it's odd. And if you get a mixture, it's neither.
So wait.
I'm
so
listening.
you only do negative x for each one to find out?
Yep.
So you
Yep.
don't do positive x?
Mhm.
Do an example of a mixture.
Tell me, is that even, odd, or neither?
I'm guessing.
How do I know? What are you doing?
Well, you gotta put the X.
To check, I got to make every x negative. Because this is a 4, what happens to the sign here? Positive, right? So I got positive 3x to the 4th. How about this one? Stays positive, so this stays the same. How about this one? So I got -5 times -x, which is positive 5x. Is it even, odd, or neither? Neither. It's not, bless you, it's not exactly the same, right? Because that last sign's plus, so that rules out even. It can't be odd because only the last sign has changed, not every single sign. So then I'd have to say this one is neither. It does not have either symmetry. Does that make sense to you? Yes, Jerome.
Basically, you can do this like this. You switching, not switching the signs, but you multiplying it off of. Like, I don't understand why that's not negative. That's a negative x. So why would that?
Well, it is, but really this was plus -5. I can change that to plus negative, and a negative times a negative is a positive.
Okay.
Because, all right, so -x to the 4th is the same thing as -1 to, okay,
Wait, I have a question.
okay.
So, why did you do positive?
Why did I do what?
Positive 3x. Not negative 3x. You change everything on negative. X was like
Because the 4 made that positive.
how? Is it-
Because this, same thing as this, and -1 to the 4th times x to the 4th. -1 to the 4th is positive
So
1.
basically, if it has an exponent, it's always going to be positive.
If it has an even exponent, it's always going to be positive. If it has an odd exponent, it's going to keep whatever sign is there. What other questions do you have?
So,
What's the homework?
I got one more thing to show you. I've been promising you for a long time we would get to asymptotes. This is the very last step of analysis that we're going to do right now. Okay. So we have two types of asymptotes, and one of them we've really already talked about. So what asymptotes are invisible boundaries, okay, that the graph will get really, really, really close to, but it will never actually touch, okay? When we talk about discontinuities, okay, it's that infinite discontinuity. That one that it gets really close to but never touches, all right? So they are, and some of your calculators graph them. I'm going to say invisible boundaries. That's the easiest way I know to describe them, okay? So, two types of asymptotes, and we'll start with the ones that you already know. And those are vertical asymptotes. All right, so these are happening when the denominator's equaling 0, okay? Denominator equals 0. But it's not a removable, remember we talked about that removable discontinuity? If I had x times x plus 2 over x times x minus 3. There are two different places here that cause the bottom to be 0. What are the two places? Right. So this x, even though a 0 would cause that to be 0, because I can cross these out, it's a removable discontinuity. Remember, if I can remove it from the equation, then it's a removable discontinuity, which is a hole. It's not an asymptote. But this one, there's my asymptote, okay? So it's when the denominator equals 0, but it does not include removable discontinuities. Removable discontinuities. Okay. So this graph would have a vertical asymptote, an infinite discontinuity at 3. And we've talked about that. We've seen that. Does everybody know what I'm talking about? Because I feel like by the time we get to this point, we're using some good math terminology, but sometimes you get lost in it too. So whatever else this graph is doing, at 3, there's an infinite discontinuity. There's a vertical asymptote. Okay. So those are easy to spot. Those are easy to pick up on. Okay. Horizontal asymptotes. That's where it gets hard. Y'all ready? I'm ready. This is the last thing. So we haven't talked, other than to leave them out of the range, we haven't talked a whole lot about how to actually find the horizontal asymptotes, okay? So what we have to look for is we have to look for the degree. And this happens when we have fractions, by the way. Okay? We have to look for the degree in the top and bottom. So by degree, what do I mean? What's the degree of anything? The biggest exponent. So we have 3 scenarios that can happen. Okay. Scenario 1, we'll put A, is that we're top heavy. Meaning the degree of the top is bigger than the degree of the bottom, because remember, I'm in a fraction, okay? Bigger than degree of the bottom. Let me show you an example. Top heavy. The biggest exponent up top is bigger than the biggest exponent on the bottom. You go with me? If that happens, and I'm going to call my horizontal asymptotes HAs, so my HAs. Okay. If this happens, then there is no horizontal asymptote at all. Okay? Top heavy, no horizontal asymptote. Remember I told you there's 3 scenarios. And have this written somewhere where you can access it for your homework, because you'll have to decide which scenario am I in, and then you just look at it to see.
No, what is AJ?
Horizontal asymptote. What do you think scenario 2 is? Bottom heavy. So if this f of x was flipped around, so if it was x squared minus 5 over x cubed plus 1, if that happens, then you have a horizontal asymptote at y equals 0. In other words, on the x-axis all the way across is a horizontal asymptote. So remember we did several functions that did this, okay? This is the x-axis. If it's bottom heavy, you'll have an asymptote right there. Then there's no asymptote at all. No horizontal asymptote. You could have a vertical, but no horizontal.
So it looks like that.
Mm-hmm. Yep. One more scenario. I promise I'm almost done, and I'll shut up talking. Top heavy, bottom heavy. What else could happen?
Equal.
Equal. They could be equal. All right, this is the hardest one to do. Same degree, so maybe it looks like this. Okay. If they have the same degree, then your horizontal asymptote is the leading coefficient. What is a leading coefficient? The number that leads the equation, the number that's hooked to the term with the degree. So it's the leading coefficient of the top divided by the leading coefficient of the bottom. So looking at the equation in pink, where would my horizontal asymptote be? And leave it just like that. 2 divided by 7. That's my horizontal asymptote. Where's 2 and 7 coming from? Right there. Okay. Horizontal asymptotes are going to impact your range. Vertical asymptotes are going to impact your domain. Okay. This is happening when I have fractions because they're rational functions, okay? All right. H dub. Golly, we haven't done in behavior yet. I'm not pushing that today.